All right, so with that said, we're going to spend the next hour talking a little bit about reinforcement learning and going over a simple code-free use case in the Knime Analytics platform. All right, so here's kind of the agenda for the hour. I'm going to give you a brief overview of reinforcement learning, talk a little bit about what it is and how it's used in some common industries. I'm going to go ahead and give a brief introduction to the Markov decision process, which is the basis on which a lot of modern reinforcement learning is built. We'll introduce a bit of notation so that you're familiar with some of the terms if you want to go and do some further reading on the topics. We'll talk about policy functions, reward functions, and I'll go through an example use case, which will be building an AI that plays tic-tac-toe. And that use case is going to include a web portal implementation, and we'll look at some of the workflows for training and deploying that as well. After that, we'll just kind of wrap up, and we'll try to address any questions you've got from there. And feel free to aim those questions at reinforcement learning. Feel free to aim them at some of the actual Knime application that we're using here. And feel free to talk to us a little bit about the web portal too, because that's kind of cool here. Okay, so what is reinforcement learning? So most of the time when we talk about data science and machine learning, we usually talk about either supervised learning, maybe some unsupervised learning when we talk about clustering or training those decision trees on our labeled data sets. So what is reinforcement learning? So it doesn't necessarily cleanly fall as a separate third category, but usually it's considered the third group here in machine learning, the third big set. So the goal here is that we design some kind of agent, this little robot in my diagram, and he's going to interact with my environment. He's going to try to interpret that environment, and he's going to try to maximize some reward. In the case of building an AI that plays games, that might be to get the high score. And that's one of the reasons why you see gaming as a very common example use case for reinforcement learning. It's kind of got a canned reward right there, ready to go. Just what's your score when you're playing? Other common environments that this reinforcement learning agent might try to live in are things like building a robot that can walk. Maybe we're trying to do some drug discovery or to monitor some network traffic. There's a lot of different applications for reinforcement learning. And the key is we need to have the ability to interact with an environment, receive some kind of feedback, and turn that feedback into a reward. Usually we're talking about something numeric in that case, like a high score. Think of how can we gamify this use case. Sometimes this agent contains a machine learning model. So sometimes this framework includes supervised learning. Sometimes there's no machine learning model at all. Sometimes we're just kind of building a lookup table as we go. Maybe we just kind of experiment with our environment. We test something, we learn what it does, and we kind of take a note of that and add it to a dictionary. There's a lot of different ways this agent can be built, and it doesn't always need to include a machine learning model. Again, just the important part is that it interacts with its environment, it receives some feedback, and it updates how it makes its choices. And we'll talk a little bit about how those choices are made when we get to policy functions. So I wanted to give a really simple example of what an agent could be. So let's say we build an agent. So this is our reinforcement learning agent, and we're just training it to play rock, paper, scissors, a really, really simple game. And let's make it even simpler and say that this agent can see my move before it makes its choice. So if I throw rock, my agent's always going to throw paper because it knows that wins. If I throw paper, maybe my agent will always throw scissors because it knows that wins. And it's just trying to maximize that score. Maybe that's a 1 if it wins and a 0 if it doesn't. That's a really small set of environments that it has to interact with. What's my move? And it's got a very small set of actions. And there's not really any randomness in what happens based on those actions. So it's very easy to put together a really simple lookup table. If I throw rock, it throws paper, etc. And through this, our agent can play rock, paper, scissors really, really easily. But of course, this is the simplest framework we could ever be trying to build an agent for. What if we've got some kind of environment that has way, way more than three options? Then we've got a really big lookup table. What if we don't have clear information about how to go from rock to win? What if nobody knows the rules for rock, paper, scissors yet? Then it's also kind of difficult to build this lookup table. So we'll talk a little bit about how to build these kinds of agents without the knowledge or the practicality of using a lookup table. So when a lookup table doesn't work, frequently we'll turn to machine learning. So some supervised frameworks are very common. Sometimes you can use decision trees. Sometimes you'll use just any kind of classifier model, or even numeric prediction models can be applied here. But most commonly, when we talk about integrating supervised learning into this reinforcement learning framework, usually we'll talk about neural networks. You'll see a lot of buzz around the term deep reinforcement learning for that reason. And there's a couple of reasons why neural networks are super exciting for this use case. It's not just because they're the cool new buzzword in data science or the cool new model to use. We all want to use neural networks. There's a few reasons why they actually are very practical. And we don't have to use deep neural networks when we're doing this. We can use really simple, shallow networks as well, and we still get a lot of the benefits. Those being, we have a very flexible input and output space when we're working with neural networks, because we need to, in some way, inform this model of what the environment state that it's in. That could be very difficult information to pass into a decision tree. If we have high dimensional numeric data, a decision tree may struggle with that a bit. There's a lot of different opportunities to slice up that data in different patterns, and that can take a lot of work for our decision tree. With neural networks, we're already talking about all of these numeric inputs. We can reshape them. We can use these convolutional spaces. We have a lot of different ways of handling input data with an artificial neural network, and that's very helpful when we're trying to abstract an environment and use it as an input in a model. Also, neural networks, of course, have the very cool ability to do a lot of feature engineering on their own, which can be helpful when we're working with these complex environments, because we might not know what features are important yet when we're trying to plug a model into, for example, some chemical analysis, or if we're trying to plug our model into a billion different IoT sensors on a robot when it's trying to learn how to walk. It might be very impractical to do that feature engineering on our own. But also, in one of the, in my opinion, most useful things about using a neural network for this kind of task is that we can train them iteratively. So this is true of several other model types, but it's also true here of the neural network. We can train this model in batches, right? We send our network through multiple epochs, normally when we're training one, and we update it multiple times, and we keep redeploying it and seeing how it performs. So in a very similar sense, we're able to take this neural network that will end up being part of our agent's decision-making process, allow it to explore its environment, pursue different options, get some feedback, and then update the weights inside of that network in an iterative fashion, continuing to improve itself. If we were using a model like a decision tree, for example, we would have to store more and more data and use more and more training data with each iteration, because it's much more difficult to take a decision tree model and simply update it, because it's based on those counting algorithms. So these models like neural networks, where they're based on these gradient updates, are very useful in these frameworks where we want to iteratively update and explore. So here are three common use cases for reinforcement learning used across industry. One you'll probably hear a lot, especially at the Knime Summit, since we have so many life scientists here, is chemical drug discovery. So let's say you are trying to build a new medicine to solve some kind of health problem, right? You need it to react with some protein and maybe not react with some other ones. So there's different ways that we could start working on that process. We can build a billion different chemical compounds. We can push them through a testing framework and just see what happens. And that's probably the way it was done way in the past, before we had the ability to apply all of these computer science and statistical frameworks here. So when we're talking about using these reinforcement learning for chemical drug discovery, we allow our agent to create these compounds, test them out, see what it does, and iteratively try to get better at producing compounds that are reactive. And through that framework, we're not necessarily going to automatically build our medication, but we will be able to significantly narrow down the set of chemicals that we really need to test in the real world. So we'll just have like a set of maybe 1,000 chemical compounds that we want to test as opposed to 1,000,000. It'll help us narrow down that to compounds that are likely to be reactive as opposed to a whole bunch of duds. So this is a way that we can kind of reduce testing spaces, as we can use this reinforcement learning process to intelligently explore research spaces, like with this chemical drug discovery. Another common use case is through things like traffic light controls. You'll see a lot of major cities shifting their lights to being on standardized schedules, like maybe it's 30 seconds green, 30 seconds red, 30 seconds green. And you'll see a lot of those control systems being shifted over to AI-based controls. And those are going to be built through reinforcement learning, because this agent can have some understanding of what a congested system looks like. So let's say how many cars are not moving at all, right? We can use that as some kind of numeric reward system. We can say we want to keep everybody moving, and we can allow this agent to control the lights through some of these networks and through some of these policy functions that we'll talk about, and iteratively move towards fewer and fewer stationary cars. So anything where we can really define that numeric reward, and anything where we're able to actively test environments, we can try to apply reinforcement learning. And there's a lot of simulation environments that we can use for this too. It's fairly straightforward to build a simulation for cars moving through a city. And we can use that simulation to train our reinforcement model. We don't have to necessarily just stick it out there in the real world and let it start from scratch. A lot of these things will come with simulations, and this can save simulation time as well. That'll be true with some of this traffic light control stuff and with some of the drug discovery. And then finally, this is probably the one we've heard about the most, is robotics. We hear a lot about reinforcement learning being used to train robots to walk, maybe training robots to pick up objects gently, to identify hands and maybe shake your hand. There's a lot of different use cases for that across a lot of industries where we're talking about manufacturing. Okay, now let's talk a little bit about the basis. So this is the framework that we're going to be talking about when we talk about building these reinforcement learning based agents. We're going to talk about them living in this Markov decision process. So on a really simple level, a Markov decision process is just some environment and action set. So we've got all of these S's kind of in this diagram over here, and these represent different states that my environment could be in. Maybe this environment is just kind of where I am in the world. Maybe S0 is I'm at home. Maybe S1 is I'm at work. Maybe S2 is I'm at the grocery store. And these are different actions, and they could take me to different environment states. Maybe when I'm at home, one of the actions I can take is getting in my car. And maybe there's a 50% chance that gets me to the grocery store. Maybe there's a 50% chance that takes me to work. So in that way, we have different actions available to us at different environments, and they will move us around this set of environments. This is a Markov decision process. Another important thing to note here is that these actions are not definite. I mean, some of them can be. You can see here that if I'm at S0, maybe that's at home, and I get in my car, there's 100%, there's one probability here that I go to state S2. So that's an action that I can take that does have a definite outcome. But a lot of these actions, and you can see that as an example over here, if I take action A0 from S1, I've got a 10% chance of going back to S1, a 20% chance of going over to S2, and a 70% chance of going to S0. So we're not talking about definite frameworks here. We're talking about something stochastic here. We have probabilities here. We don't have a direct line into future states. So this is the theoretical backend that we use when we're talking about modeling kind of real world situations here. Of course, I don't know that there's going to be a definite outcome based on my current action sets. Okay, so Just keep that in mind. We're always talking about actions that have probabilities of outcomes here. There's never going to be if I do this, then I definitely get to get to work. There's no 100%. Maybe it's 99% chance that I get to work if I get in my car. Maybe it's 50%. But remember that we are including those probabilities in our framework. Okay, now I want to introduce a little bit of notation. So we talked about the actions and the states. So these A's, these lowercase a's, are going to represent an action taken. S is going to represent my current state, so where I am before the action. So from state S, I take action A. And that will move me to state S prime. S prime could be the same state as S, as we talked about with A0 over here, or it could be a new state entirely as S0. Now we're going to talk a little bit about some of these terms that are more specific to reinforcement learning. So we said earlier that for us to build this agent, we need to have some concept of reward. And that is, how happy are we? How is this a good thing that we moved from S1 to S0? Is it a bad thing that we moved from S1 to S0? We need to have some kind of way for our agent to understand if it's doing things that it wants to be doing. And that's what we're going to call our reward function. So this is the reward function here. And you'll notice that it's based on three separate things, actually. We have our action A, our past state S, and our future state S prime. So it is definitely important that we remember that this is not only based on moving from state S to S prime. It's also based on the action we've taken to get there. And one example I like to give for that one as to why that's important to keep in mind. Imagine I go to work. So there's definitely a reward associated with that. For me, I get paid, right? If I take my car there, then I get that full reward. I didn't spend too much money getting there. If I like charter a helicopter to take me to work one day, then maybe that reward's not as high because I've spent so much to get there. There could be a cost associated with these actions that mitigates that reward that we get from moving from state to state. Or those actions could have value in themselves. It just depends on the environment that our agent is living in. Okay, and just like we had the reward function, this capital R based on A, S, and S prime, we also have the probability function P. So this is the probability of going from state S to S prime. So for example, the probability of going from S1 to S0, if I take action A0, is this 0.7. So when you see this notation, that's what that represents. And then down here, finally, we see these capital A and capital S's. Those are just the states of all possible actions in all possible environments. So in this case, we really only see the A0 and A1 actions that would compose set A. And we see the S0, S1, and S2. That's our set of possible environment states, S. And then finally, we have a policy function, and that's going to define what action our agent takes. So maybe that could be something really simple, and maybe that just means that agent always takes action A0. And that wouldn't be that interesting. We would go from S0, we always take action A0, we either go back or go down here. And then again, we just keep taking action A0. And we wouldn't learn much from doing that. We wouldn't have an agent that's capable of much growth. So another common policy function might be to take a random action. And this is a really common policy function to use at the beginning when we're trying to train an agent based on some machine learning model, like a neural network. We might want to embed some randomness into the action choice that our agent takes, just because we want to explore that environment more, right? We need to kind of balance that exploration of our environment and kind of exploitation of our predicted rewards, right? We talk about that a lot when we're talking about intelligent selection of data labeling and stuff like that as well. Okay, so let's talk again a little bit more about policy functions. So as I said just a moment ago, these are how we define the choices our agent will make. So maybe in a really simple framework, it's kind of like our agent having a little map. Depending on what square you're on the grid, move in this direction, and that's just what you do. In this case, that policy function is a good one. It takes us to the reward, avoids the death space, but that policy function is not going to be perfect all the time. Just keep that in mind. But it is kind of like this. It's a map that tells our agent what action it wants to take given its current environment. Okay. So here's some just really basic examples again of policy functions. We talked a little bit about this bottom one here. Maybe our agent is just taking a random action, and we're using that to force our agent to explore and learn new things. Maybe our agent just always says hit me when it plays blackjack. Again, that wouldn't be a very effective strategy, but this would be an example of a way that our agent makes decisions. And do keep in mind that while our agent is deployed, these are usually constant functions. So they just stay steady. So this policy function isn't going to change as our agent moves around this board. So it's just simply based on the environment state that our agent is currently in. So typically when we talk about training an agent, we allow this policy function to explore its environment. It just kind of plays the game for a while. It creates chemicals for a while. It tries to walk for a while. It does whatever it does, just based on the policy function that it has. And as it does that, it collects data. It collects information based on that reward function that we've supplied it with. And then after that, we can allow our agent to then go back and update its policy function. So we'll give our agent a policy function. We'll allow it to explore its environment. We'll then come back, use those rewards that our agent has discovered while exploring, have it update its policy function, and continue cycling through that process where we explore and update and explore and update. And again, you'll see this pi symbol to represent that policy function. Okay, now we'll talk a little bit about reward functions. So there's a lot of different choices to go through when you're picking out reward functions. And again, this is why gaming is such a common example use case for reinforcement learning, especially when we're just playing around with new frameworks, new strategies for training our agent, or even new network architectures if we're using deep learning. And that's because, like, if we're playing Pac-Man, for example, there's a score displayed right on the screen. We know what our high score is. We know what our reward for our agent is. We want it to see that score grow, right? It's very straightforward. We don't have to do any real work to get some kind of reward. But most of the time when we're trying to deploy reinforcement learning into real world applications, this is where a lot of the hard work goes into. There's a lot of kind of pre-canned reinforcement learning frameworks that we can deploy, but we do need to come up with our own our own reward function. Maybe we're life scientists and we're trying to create stable chemical compounds. Maybe our reward function is the percentage of compounds created that were stable, or maybe it's the average lifespan of those chemical compounds. These are both kind of ways we can look at how well our agent is performing numerically. So we do require some kind of reward function to allow our agent to grow. And those can be difficult to come up with sometimes, and they're going to vary by use case. Again, if we're talking about robotics, we might be talking about how far did the robot walk before falling over. If we're talking about building maybe a reinforcement learning based agent that contacts our customers and it tries to be really friendly with them, maybe we can use a reward like how many people responded. So there's a lot of different ways we can build these rewards, but it is kind of unique to this idea of using reinforcement learning is that we have to have these useful rewards. They're almost like measures of success in a business use case. If you've got KPIs, maybe we can translate some of those into reward functions by modifying them a little bit. So this is where a lot of the effort goes into, is finding a reward function that not only makes sense to us as the data scientist, but also makes sense to our agent. So one thing that you'll see a lot with these reinforcement learning agents is that they don't always use one reward function. Maybe they have multiple reward functions and they're combined in some fashion. Maybe at the very beginning, when you first start training this agent, you give it a really simple reward function. Maybe that's just send out emails successfully. Maybe that's the reward function that you start with. How many emails did you send? And just allow this agent to kind of learn how to send emails. And then later on, once it's pretty good at that, maybe we shift our reward function. And it's no longer, did you send enough emails? And now it's, did you get responses on those emails? And that's another reason why neural networks are a really cool type of model to use for this, is because we can very easily change what our loss function is, or what the reward function is there when we're updating those kinds of models. So now I want to talk a little bit about today's example use case. So I've built a reinforcement learning model, an agent here, that's going to play tic-tac-toe. So the way this works is we've got this, this neural network that is embedded inside of this agent. And what that agent is doing, what its policy function is it's going to look at the different options of places it can play on the board. And it's going to try to predict its chance of winning based on each of those play options. And then its policy function will say, take those chances of winning and pick the highest one, right? So our policy function isn't strictly that neural network, but it does contain it, right? So what we're doing here is saying that our agent will pick the place that it thinks it's most likely to win. And then as it goes through, it plays, it learns which moves were successful and which moves were unsuccessful. It can update that neural network inside of its policy function that says, okay, this one was actually did not have a very high chance of winning. And this play down here in the bottom left was maybe a better choice. And in that way, we're updating the policy function without really changing too much of what it means to us. It's still selecting the play that it has the highest chance of winning. And we're going to show and demonstrate a playable application on the Knime web portal. So you can see a little screenshot of it down here. So this is the first page of that web portal where you can play against this tic-tac-toe agent. Okay, so here is the training of the AI. Here's the workflow that I used to train the AI. So up here at the very top, you can see the definition of the network architecture I use. Now, I don't know if this is the ideal network architecture. There's a lot of ways we can play around with this. There's a lot of different ideas here. But this input space is this 27 length input space, this 27 length vector represents that tic-tac-toe board, which is of course the 3x3 grid. So there's 9 spaces on the board. Those spaces can be empty, have an X or an O in it. And that then represents that 27 length binary vector. And that is our environment. So this is just me passing in my environment state. If I had a significantly bigger board, for example, if my environment was maybe the entire screenshot of a video game, I might have a much larger input space, just like using an image to do some image analysis. Maybe I would then leave that input space as that default kind of unflattened tensor, and then use some convolutions over that. So there's a lot of reasons why this flexible input space, as I mentioned earlier, is really useful. But in this case, I'm just using that 27 length binary vector. And then we're using some, just 2 dense layers here in the middle, both 54 units of TANH activation functions. And we're putting in a little bit of dropout here as well. And that's just to help with some regularization. I'm trying to prevent my model from overfitting because again, it's just playing against itself here. And I'll explain that a little bit when we get down below. But since this model is playing against itself back and forth, I wanted to make sure that it didn't learn any patterns too strongly. Okay, and then finally, it just has this 1 unit output space, and that represents the expected reward. So my agent is trying to predict its reward. And that reward is something that I calculate after the game is finished. So what I'm using for a reward here for this network is how close to a winning or how close to a losing game were you? If this was the winning frame, like this move wins the game, maybe I use a 1. If this If this play immediately loses the game, maybe that's a 0. So I've got different sketches on there. And if you're, for example, 4 moves away from winning, I kind of pulled that back down a little bit from 1. And you can see that specifically in this math formula node. So this is available on the hub. If you want to download it, run it, play with it, improves the model architecture, etc. But what it's doing down here in this reinforcement learning process is we're using this fairly new loop. It was added this year, and it's called the active learning loop. So it's got a few different ways you can use it, but the most important thing about it is that it's a recursive loop that has a model port. So we do have the regular recursive loop that just has the 2 data ports that get passed around and in circles, and you can keep doing something until it's finished, right? So we have a lot of different ways to do these recursive loopings. But this active learning loop, which was intended to be used to train a model and then let that model then inform the end user of useful data points to continue labeling. So if we wanted to do some data labeling, we would use this active learning loop. And there's examples of that on the hub, but I'm using it here just because it's recursive and has this model port. Okay, so what happens inside of that reinforcement learning process that I'm using this active learning loop for? So the first thing that happens is we play a set of games. So this is going to kind of go, we'll go in from the inside to the outside. So when we're playing a game here, what happens is this network comes in. So again, this is just my regular network. It's not been updated. It's got its default weights still, and it comes in here and it just gets run, right? I can just run this neural network on input data already. I don't have to train it first. The outputs are going to be kind of nonsensical, all right, because they've not been, this model hasn't been trained to do anything yet. But that's how it's selecting its first moves, is it's with a kind of 50-50 ratio, and that adjusts over time. It's either selecting a random move or the one that the network thinks is most useful. And in that way, it's placing an icon on the board. And this network is recursively playing opposite sides. So it'll play X and then it'll play O. It'll play X and then it'll play O. And one of the advantages to training an AI like this against itself, as opposed to just playing it myself over and over again, is kind of twofold. Of course, it's going to need to play quite a lot of games, and I don't really want to sit down and play 1,000 games of tic-tac-toe. And also, at every stage in its training process, it's going to be playing against somebody who has roughly equal skill level as itself, right? Since it is just playing against itself. And this is true in really just about any process where both sides kind of have an equal chance of winning. So whether or not that's true in tic-tac-toe, it's probably up for debate. Not sure if it's better to go first or second, but that's the idea here, is that it's playing against somebody of relatively equal skill. So that's why we want to let it play against itself. So it's selecting that move, it's going through that loop, and there's some testing that's happening over here in this game over component, just to check and see if one of the win conditions for tic-tac-toe have been met. Those being, of course, did you get 3 in a row in a did you get 3 in a row in a column? Do you have your diagonals filled in? And of course, is the board full? Like, have you just tied the game out? So in that way, we're playing a single game. We're logging those board states with how close they were to winning, losing, or tying games. And then we play a full set of games. So in this case, I believe I'm training this network to play 100 games here. So it plays 100 games. And then we have all of that labeled data. We have all of that information from our environment that with those reward functions that we've built in. In this case, that reward function, again, is being how close to a winning game was it? How close to a losing game was it? And we use those labeled board states now that we've retrieved from exploring our environment. We feed those into our learner. So in this case, the Keras network learner over here. And we update our model based on what it's learned exploring that environment. And then we go through here. There's a little bit of housekeeping where I've deployed the model again over here just to score it because I wanted to track those scores over time later on. And then the recursive loop body starts over again. That now updated network model. So it's seen 100 games, it's updated itself based on them, moves back to the start over here. And again, it starts playing against itself, now slightly better than before. It runs through that set of games, it updates itself again, and it keeps doing that over and over again. So here we've trained the model 25 times, each time on 100 sets of games. So that's how we're using this active learning loop to do some reinforcement learning. Okay. And then of course, there's a second workflow that I've built here to generate the actual web portal application because I wanted to play against it, of course, if I was going to go through the trouble of building this network. And you see a pretty similar framework here. We've still got these loops in here for playing the game, but now it's kind of split into two boxes here. Either the network makes a move or the player makes a move, and it just kind of alternates based on that. Another thing I want to note over here is that it's loading two models. So I'm actually bringing in two separate models here. And it's really easy in this case to build an easy mode AI and a hard mode AI. Because again, I've trained this model for 25 sets of 100 games. Maybe that's my easy mode model. It's only trained on 2,500 games. Maybe my hard mode model has trained on 10 times that many. So in that way, I can kind of easily make an easy mode AI and a hard mode AI, just based on how long it's trained for. Another way we could make those AIs different is we could change their architectures. If we wanted to just have AIs that behaved a little bit differently, we could train them separately, train them with different starting conditions. And there's a lot of randomness in there. So building AIs in this fashion kind of gives us different personalities in a sense. We'll walk through a little bit about what this looks like when we open up the Knime web portal so you guys can see what it looks like when it plays. But what's happening down here is we have a couple loop bodies again. So starting from the inside, again, these are just where the network takes its move. In this case, we just have a switch. Should the easy mode network or the hard mode network make the choice? And again, that's just based on that policy function. It takes the input that was the 27 length binary vector representing the tic-tac-toe board. That generates predictions for win probabilities based on those available moves. And then our policy function says, pick the one that we think is going to win, is most likely to win. And then that's how that goes through and makes its choice. Down here, of course, it's slightly different. And I'll show you this in the web portal. But this is just presenting you with a visual tic-tac-toe board. And you can just check a box and make your play. So that's how we're going through on that. And of course, we have to do this loop here. It's a recursive loop. It keeps prompting, alternating between the network and the player to make them move until, again, a game over win condition is met. At that point, we'll end the game, we'll display some win screen, and we'll prompt the user to play again. Another thing that's happening over here that's really useful is that we're saving the game data. So when I was training the model originally, of course, I had it play against itself. And that was useful when the model was really bad, because it's not going to learn much if I just destroy it over and over again, right? It won't really see much there. But now that it's good enough to at least play a real game of tic-tac-toe, it can benefit from playing against different players, explore some different strategies, right? So what I'm doing here is I'm saving those board states and those rewards, just like I was at the training time, and logging those into a spreadsheet that I can later use to update my model as it learns from playing against real people. All right, so with that, I'm going to shift over here really quick, and I'm going to show you a demo. All right. There's my web portal. All right. Oops, that's my slide. They look the same, so it's confusing. This one. All right. Now we have it actually in the web portal. So here we're just up on the Knime web portal. This is the new version of the web portal. You can see it looks a little bit different at the top. Doesn't have that slider off to the side. And some of the buttons we have to navigate are a little bit nicer and cleaner. So this is the first page that this application shows when we go through to play. So I can select the difficulty. Maybe I want to play against easy or hard. maybe I want to go first, or have the name Knime AI go first. And we just kind of go through that. So I'll select hard and I'll let the AI go first. Let me try that one more time. There we go. Little hiccup, but that's okay. So it's kind of interesting. The hard mode AI always makes its move first in the center. I'm not quite sure, I'm not quite an expert on tic-tac-toe if that's the best move, but it is interesting that it makes a different first choice than the easy mode AI. I think the easy mode AI always starts down here. And that makes sense because I'm no longer using that randomness when I let the AI make its moves. When I've moved it into this kind of, I guess, deployment architecture here, I've removed that random part of its decision-making process because I'm no longer really pushing my agent to explore its environment. I just wanted it to do its best to beat me. I'll do the exploring by being the human counterpart and making different choices. So I'll play this spot. And you'll see that I've made my move down here and the agent has chosen to play straight down. So of course, I'll block it. Now it's made another play over there. I think this one will probably end up landing in a tie. I don't think it's got me anywhere. Yep. Okay, so that's an example about how we've built an AI to play tic-tac-toe. And again, at no point did I do any hard coding on telling this agent how to play tic-tac-toe. So the actual decision-making process has no logic embedded by me, except for that make the move that you think is most likely to win part. The only logic that I've had to code into this is the definition of, has anybody won? So when we get to these board states, it's checking to see if anybody has won. And that's the only thing that I've had to code as far as logic. And of course, when I say code in this situation, I'm just talking about building my Knime workflow. Okay, let's play one more time and look at the easy mode AI, see if it performs any different. See, it does start in a different spot. And again, that's kind of an interesting way. If you want to have multiple AIs here with different personalities, is you can train them with different architectures or at different amounts of time. And even if they have similar performances, they might behave differently. I'll play there, whatever. Okay, so it's at least going for the win still, that's good. Oh, no, the easy mode AI's got me. I think I made the wrong play in the beginning. Got two directions. Maybe it won't take it. No, it didn't take it. Okay, perfect. See, there's our easy mode AI not picking up things. In this case, I beat the AI. All right. So I'm going to walk through the workflows really quickly, so you can see what those look like as well, as opposed to just having those screenshots. And then we'll open up for some questions before we wrap up in 15 minutes. Okay, so here's the two workflows, and these are going to be available on the hub. You will get the slides after we wrap up this call, and that has links to everything that you'll want to see later. So just look for those in the final slide. But here's that framework for training the model. We just have these different inputs. So again, we're using some of this Keras integration, where I'm just defining the shape to be 27 inputs, and those inputs being floats. So in this case, those are really zeros or ones, but that's the data type that I'm using for this. Just have a simple, oops, I have updated that. It's no longer 54. It's now 100 units of TANH. So I've been trying to make it a little bit wider to give it a little bit more ability to understand more complex features on the board. So this is currently 100 unit wide with TANH as its activation function. So you can see in this way that it's really easy to go through and define my network architecture. So I've done a lot of playing with different shapes, different architectures, and I don't want to make it too big because I don't want to have to train this model for days, but I don't want to make it too small because it needs to be able to understand some more complex features that are existing on the board. So there's a balance to walk So I'm curious if anybody will download this workflow and come up with some interesting architectures that do really well. And then of course, here's the dropout. I'm just using a 0.0 or a 0.1 dropout rate here. And this is what this does, this dropout rate, is it, as it goes through here, it kind of shuts off 10% of the neurons as we run through. And this is helpful because it gives us more variety in what happens with this network. It kind of keeps us from strictly relying on individual pathways as we run through that neural network. And that's useful because it helps us generalize. It helps us prevent overfitting to the training set, which in this case, I wanted to do my best to mitigate, since we're going to be, at least at the very beginning, playing some very boring games of tic-tac-toe where the agents are just kind of dropping icons all over the board. And again, I've used that dropout and I've applied it to both of these layers. So when I use this dropout layer, it applies to the previous layer in the chain. And then my final output is just that 1 unit, and I'm using a sigmoid because I want that output to be between 0 and 1, right? So I'm just picking what my output space should look like, making sure that we pick something that maps up appropriately with whatever reward function we're choosing to use. All right, and that runs through here. We have our active learning loop. Again, this was just really cool because it's basically a recursive loop that has this port for model. So it lets us recursively deploy and update models in this framework. Down here, we have some of these components down here. Our model is selecting its move. So before I allow the model to select its move, what we go through and we do is we make sure that I limit the list of playable moves. So, and that's really simple. It just means that you can't play an X where there already is an X. You can't play an X where there's already an O. You can't steal your opponent's spot. That's basically the idea. And it double checks to make sure that the board's not full too. So there's different ways that we're just kind of making sure that we're only displaying playable moves to this network, because really it doesn't care, right? It's just kind of taking this input space and generating these numeric predictions on top of them, and we're selecting the highest one, right? So it'll generate those predictions on any input space, even if it's not a legal board. So I'm doing that limiting down here. All right, and it kind of gets over here, and let's see how long it takes to set that there. Actually, let me cancel this really quick. I want to show you what the Keras network learner looks like. So instead of playing 100 games, we'll just play one for now. That's fine. So that goes through here. The recursive loop plays until the board's finished, somebody wins. And then that keeps repeating until the number of games that I've defined here in the counting loop is reached, in that case, 1. That data comes through. I'm giving some scores to these boards, and we come up here into the Keras network learner. So in this case, the input is just my column, which I've named list. And this is just that transformed board state. It's just that 27 length vector with those binary values that represents the tic-tac-toe board with its 9 space grid and empty X or O options on top of it. So that's my input. And then my target is that score. And I'm using a mean absolute error to try to get it as close to that as possible. There's different loss functions we can play with. It might even be good to try to start switching those loss functions for different iterations of this training process. But mean absolute error is what I've chosen here. Okay, that runs. The model trains, and we can even watch this model, which is a cool feature when we're using the Keras network learner. So in this case, it didn't take long to run through it because it's not really training for all of that long per execution. And in this case, of course, we only played 1 game as opposed to 100. So we can see and we can monitor that loss function as the model trains, which is just a really cool feature of the Keras integration as opposed to anything really reinforcement learning based. And that runs through. That active learning loop happens several times, and we see that agent get better and better. Of course, in this case, while I'm running it, remember that each execution is only playing 1 game as opposed to that full set. So if you do download this workflow, and you do choose to run it yourself, just keep in mind that when it's set to its default 25 sets of 100 games, it does take a little while to run. So that's not going to be something you'll really watch run. You can set it going and come back in maybe a couple hours, depending on the machine you're using, and take a look at it. Okay, I'm going to cancel this so it doesn't run in the background. And I also wanted to show you this workflow. So this is a slightly different version of it. I've been playing with it a little bit more, but it does have all of the key parts in it. So this is the workflow for the actual web portal application, right? So in here, we see that first page. This is the first page here where we saw those rules, right? So that was that first page that comes up, and I believe I can open this and show it here too. Yeah, so this is that first web page where the user is prompted, do you want to play hard or easy mode? Do you want to play against the Knime AI, or do you want to go first, or should the AI go first, right? And that's just a set of all of these widget nodes, right? So I've got some selection widgets in here for selecting if I'm first or the agent's first. Another selection widget in here for hard mode or easy mode, and then a few little text output widgets just to kind of put those explanatory rules and different things up there. That just looks like this. So I'm going to say that I go first. I'm just going to change it to that temporarily because I want to show you down here too. And this is the component in the workflow where the user is prompted to select its move. So that's this interactive play. So that did not want to load for me. So that's okay though. This is where you would see the tic-tac-toe board, that 9x9 grid, where we saw those different icons pop up for either the Knime agent or the human player. But what's inside of here, I think I just need to restart my Chrome thing there to make that work. It's just this. So again, it's just a few text output widgets to kind of make the page look pretty. And what I'm using is a tile view in here. So this tile view is, okay, there's the one that doesn't want to run. Okay, so this tile view is just popping up with this little display right here. So this is just 9 different tiles that are either displaying the Knime icon for the AI or this little human icon for the player, and drawing out a board that way. So there's a lot of ways that we can use some of these familiar Knime nodes to build more complex web portal applications. So feel free to take a look through some of this. It'll be available on the hub. Even if you're not interested in the reinforcement learning part of it, if you just want to build a nice, cool web portal application. All right. So with that, I'm going to hop back to my slides. We'll wrap up a little bit and I'll take any questions that you guys have. So yeah, here's just our conclusion. We talked a little bit about reinforcement learning. We introduced just the concept that it's an agent exploring in an environment. It brings back those rewards, and we use those rewards to update something called our policy function. That's what we use this PyVest for, and that's just how our agent makes its decisions. That could include a machine learning model, like a neural network in our example, or it could just be some lookup table that we grow constantly. We talked about neural networks being a very popular model for reinforcement learning, partially because of their ability to accept complex input spaces, do some feature engineering on their own, but also because they can be trained iteratively very easily. And we looked a little bit about how some of these Knime tools can be used to create those kinds of solutions and how we can put them in the web portal as well. So we've also got we were already at the fall summit, so I'm going to remove this. You've already made it. But we've also got a book code for you here. So this is just Fall Summit Workshop. If you go to the Knime Press, you can download any of our books there for free using this code. And this is a link to the blog post. I've written a full blog post basically on this use case, and you can read that for a little bit more detail. And feel free to add me on LinkedIn, send me a message there if you'd like, and we can talk more. Here's a few links for some additional reading for you guys. You'll find some of these referenced in that blog post, but I wanted to just include them here as well. Notably, you've got these 2 links here at the very end, tic-tac-toe learning workflow and playing workflow. So those are going to be links up to the hub where you can download and play with these workflows yourself. And you'll receive these slides shortly after the call, and you'll be able to go through those links from there. All right. Thank you, everybody. Do we have any questions?
Yeah, we do, Corey. We have one that one of the folks missed the detail on how the Knime workflow determines whether the game is over. The game over node doesn't
Yeah.
have a model input. What does that component do?
Yeah, I'll actually go back and share that. I can show you guys really quickly. But what it's doing is it's just looking at that tic-tac-toe board, and it's looking at, let me find the right thing to share. I'm trying to talk and move my share around at the same time. So let's look at it over here since this is a bit easier. So this is the component you're talking about. It doesn't have a model input port, that's correct. So this is just the logic that I'm using to check if the game's over. So I don't necessarily want to promise that this is the cleanest way to do it, but this is the way that I had implemented it. And what it's doing here is it's taking that tic-tac-toe board, it's looking at, for example, the first row of the board, and it's looking at, so it splits it up into that, basically that 27 unit tensor. So in this case, it's a 3 by 3 by 3, pretty much a cube, yeah, of which icons are at which board state. So say we have, then I can extract from that a vector that represents just where the x's are placed. So what I'm looking then is to see, are there 3 x's in the top row? Are there 3 o's in the top row, et cetera? And I'm doing that just by summing up those binary values. And if any of those possible combinations sum up to 3, I'm calling the game over, right? So if anybody's got 3 in a row, if anybody's got a 3 in a column, or if anybody has a 3 in either diagonal, then I'm saying that the game is over. Or of course, if the board is simply full. So that's what's going on in here, is it's looking at that board state. It's counting up how many times X is played in the first row. And if that value is 3, then it's game over. Hopefully that answers the question.
Thanks, Corey. I did also miss part of that question was actually a statement, brilliant presentation. So
thank you.
Wanted to pass that on as well.
Very much appreciated.
I know you've mentioned that the slide, that the video or slides would be provided. So I think we've answered that. Is there any other detail on that?
You should get both of those. I don't want to promise exactly when you'll get them. I know we've had some really great organizers, so you might get them today if you're lucky, but I'd expect them tomorrow.
Next question.
Or maybe Monday since it's a Saturday. Ooh.
Yeah. Next question is it possible to let 2 agents, beginners, play and learn from each other?
Yeah, so that's exactly how this model is learning on its own, actually. So what we're doing right here is this model is actually playing both sides of the board. So in this learning workflow, what I'm doing here to make it easy for the model is I'm actually letting the agent, first it plays X, right? It places some icon on the board. It goes through. And what I'm doing between each iteration of this recursive loop where it's playing the tic-tac-toe game is I'm actually switching the labels on X and Y. So as far as the model is concerned, it's always playing X, but in reality, it's playing opposite sides of the board with every turn of the gameplay. So yeah, that's exactly what it's doing in here. And that's a good choice when you're training these kinds of agents because you do want them to be learning against opponents of equal skill, or at least roughly equal skill. Like I said at one point, if I had just started playing this completely untrained network from scratch, I would just destroy it at tic-tac-toe because I'm pretty good, and it would never really get a chance to learn anything. So yeah, it's a good strategy.
Great, and one final question. Can the model learn to trap the user? Is the possibility of learning this determined by the score definition? Do you need to reward the model for that explicitly?
That's a good question. And I suppose that depends on what your goal for the agent is. In this case, I'm not giving the agent any explicit reward for arriving at a tied game. Because I'm really trying to push this agent to actually win. But if that was the goal, and if that was the most useful thing in your framework, you could adjust your reward function to try to encourage the agent to arrive at a tie. Maybe arriving at a tie in your use case is just as good as winning. And in a lot of use case frameworks, I'm sure that's actually true. But that would just come in when we're talking about defining our reward function. So at one point during the presentation, I said that that was the most important part of this framework, picking and choosing and designing your reward function. And I think that's especially true in your example question.
Great. That's all that I'm seeing right now in the chat.
All right. Well, we're at time too, so that was perfect. Thank you for the questions, everybody. Appreciate it.